Hello, everyone. While the people are still coming, thank you so much for coming to this talk. I hope that you're having a great time at KotlinCon 2026, and I'm going to try to make it a little bit better. So first, who the hell am I? My name is Marat. I work as a Kotlin language designer at JetBrains, and I hope that I'm a bit known for being one of the co-authors of the Kotlin language specification, so I know a thing or two about the language. And some of you might remember me from KotlinCon 2025, where I already talked to you about a very similar topic. Specifically about a deeper dive into shallow and deep immutability and how it's slowly coming to Kotlin. So in 30 seconds, that talk was about multi-field value classes coming to Kotlin, where you can declare now a value class instead of a data class with multiple fields, and you can work with this thing as you would with your mutable in-place data class. So you can write reassignments, you can do plus assigns on its fields, but under the hood, it's compiled down to a copy and update that uses a compiler-generated wither for you. So the talk last year was about why we're going for this, how it maps to shallow and deep immutability, and that this thing is basically up-and-coming value semantics in Kotlin. So I already talked about what I'm going to talk about today, so why the hell do I even get this talk? The thing is that we're actively listening to our community, and after the last talk, and after we published the first design notes and design proposals on multi-field value classes, we got a lot of feedback that disagreed that this is something that people need. And this is just a quote from one of the Reddit posts that we got after we shared the Kotlin value classes design. And this piece of feedback is great. Like, it might look like this is just some people rambling about that Kotlin is going the wrong way, but actually this is awesome. We really like feedback like this because this feedback, unlike some kind of a feedback that doesn't give you anything constructive, this is actionable. Every point that a person raises here is something that we should talk about. So they're talking that Kotlin is turning into an academic language, so they're kind of like raising the question of, is value semantics something that Kotlin even should try to adopt? Is this something that Kotlin should have at its core? They're talking about that the copyvar update that I showed you on the previous slide that does wither update under the hood, that is going to hide some side effect from you, so it's going to create problems in code comprehension. And this is the second point that is worth talking about. And the third point that they're taking is that, well, this design is horrible because you're going to do reallocations all over the place, and that creates problems for performance. So basically, the design is flawed. You should reconsider doing value classes. And I'm going to try and talk you through each and every of these points and try to convince you that actually you should stop worrying about value semantics and that it's coming to Kotlin, and you should actually begin loving it and begin adopting it. So what I'm going to talk specifically about today is we're going to go through first a short recap of what I mean when I say value semantics, and how you, without probably even knowing about it, you're already using it every day, or almost every day, or your agent uses it almost every day. The second is I'm going to talk about the problems that actually happens in your code if you deviate in some domains or applications from using value semantics. Third, I'm going to talk about the design that I just showed you for pragmatic updates and why this design is actually good for readability and not problematic. And fourth, in the very end, I'm going to spend some time talking about performance, and that actually with value classes, you should not be afraid of these extra allocations that you think you pay for, because actually, as it turns out, there are almost none. So let's dive right in. First, what do I mean when I say value semantics? Previously in coding, probably you have written this code several times, maybe dozens of times or hundreds of times over your career. This is a pattern well known in Java, widely used in Java, which is defensive copying. So when you cannot trust something that no one will hold the reference to a thing, you have to copy it going in, and when you give the reference out, you also have to defensively copy it out in some shape or form. And unfortunately, Kotlin saves you in a lot of cases from doing this, but if you really cannot trust who can call you or who calls you, then in Kotlin you need to use the same pattern of doing the copy as you take some data in and as you give some data out. And if you actually squint a bit and if you take a real look at what this thing is actually value semantics in disguise. And I'm going to show you what I mean by that in just a second. And there are basically like two opposite views on the defensive copying as a thing. Some people say that it's horrible because you can easily forget it. And if you forget it and someone abuses or uses incorrectly your data, then you basically have bugs and problems. And it's also horrible because it hits on performance, because you have to create new list instances going in and going out. Some other folks say that it's actually great because if you do this, if you carefully follow defensive copying throughout your code, then it simplifies your code comprehension because you don't have to think about who actually holds the references to different things, because you know that no one can. Like, I'm the only holder of this thing is for me, it's mine. And this property, it makes certain kinds of bugs not possible, as we'll see further down in the talk. So actually, but what is value semantics? So again, in 30 seconds, value semantics is saying that your data has the property of only data matters. Only the things inside your boxes matter, but the identity of the boxes, the references that you hold to them, they don't really matter. So like, again, very simplified. If you have two instances of some data type that hold the same data, you should only care about their equality in a sense of a structural equality. You should care that these two complex numbers hold the same real and imaginary parts, and the double equals say you that, yeah, these things are the same, and the triple equals, the referential equality, it just should not matter. You ideally, and currently for inline value classes in Kotlin, for example, you cannot do this. This is prohibited by the compiler. You should not care about identity of things that follow value semantics. And consequently, if you try to change those things, if you change a thing to a different value, values become disassociated. They're different. So if you change the real value to 3.0, it's now a different thing. If you change the thing, but the imaginary value stayed exactly the same as 2.0 as in previous slide, the thing stayed the same. So yes, there probably, in the current Kotlin and the current Java, there would be a new box created, but you should not care if you look at these data from the point of view of value semantics. If you want to go deeper into what value semantics also brings you, I highly recommend you go and watching the good old data talk by Andrei Zaitsev from the previous Kotlin Conf. That talk is very insightful and very in-depth about what you actually get from adopting and following value semantics. It will do a better job than I can try and squeeze in 30, probably now more than 30 seconds. But to put some pictures into your minds, like reference semantics is something that we use all over the place. And that basically means thinking about the boxes. And if you have two references to a box and you change something that lies inside the box, both references see this thing. So if you do an in-place update, if you follow reference semantics, both references will see the change. So your things are mutable. They're in-place mutable. Updates mean everyone that can see this reference, can see this value, everyone will see the update. With value semantics, you just cannot do this. So you can take a look and you can view value semantics as everything is immutable by definition. It is a bit of a flawed view. I'm going to explain a bit why there are asterisks and terms and conditions applied. But for now, you can think that value semantics means that everything is immutable. And if you want to create a new thing, you need to create a new box. You need to reassign your reference from the old thing to the new thing. And that's it. The original reference stays pointing to the old value. The new reference with the new data points to the new thing and the new object. And this thing is practical because besides defensive copying, you are already knowingly or unknowingly using value semantics every day. So when you have an immutable data class and you're moving and creating new instances of it around with copy, you are actually using value semantics If you're using Kotlin X collections immutables, and in a lot of cases you will be using those, you are also following value semantics because immutable collections follow the same principle. To create a new state of the collection, you will create a completely new value. If you're working or interrupting with Java records or unmodifiable collections on the Java side, they also look like something that adopts and uses value semantics. And a lot of the APIs that, again, you are using in your day-to-day work, be it Guava, be it Yoda Time, which was created with the idea that the time APIs should be based on immutability on value semantics, like jog, many other APIs. In a lot of cases, they are value-based because this brings a lot of benefits. And the thing is that we already do value semantics. In a lot of cases, we just don't call it that because we don't have to call it value semantics. Sometimes we call it immutability. Very often, you will call it stability because, as most of you probably know much better than I do, that Compose performs best when your state behaves like values, because value semantics and property that UI state is immutable and all updates to the state are trackable by the Compose, this property allows to do performance recompositions. And actually, again, if you take the value semantics view on what Compose cares about, then the stable types that the Compose compiler infers for you and marks, like this type is stable, this type is runtime stable depending on the generic, and so on and so forth. These types are fundamentally value types. They also have this property of, if I want to update something inside this value, I will create a new thing, and Compose will definitely know about this, because there will be a new reference involved. And for reference-based types, types that don't follow value semantics as carefully and as closely, there is a bridge in Compose, which is mutable state, and that's basically a thing that allows you to say that, well, this thing can be mutated in place, but at some specific snapshots when updating the bridge, when updating the mutable state, that's the snapshots when I'm going to be taking kind of like the value semantics viewpoint on this and make Compose know about it. And Compose had to do quite a bit of work. They basically had to build a parallel type system for value inference, value semantics inference, to get this knowledge about your types, to get performant and efficient recompositions. And if we had value semantics built into the language, so for example, value types, then for those types, Compose could do a better job of better recompositions and all of those things. So about the bridging two worlds, just to give this a bit more concrete example. So if you have, for some reason, in your Compose application, some plain old reference type, which is mutable in place, some kind of a user where you can have an update to the name, then to make Compose know about updates to this thing, you wrap it into a mutable place, mutable state, sorry, and at this moment, you basically give this thing value semantics. You say, well, from now on, this thing is going to be tracked when you try to update it. And when you update it, the Compose will check, well, has the value actually been changed or not, and trigger a composition if it needs to. On the read, again, if it knows that the thing hasn't changed, it knows that it can skip the specific portion. And as a result, this reference type participates as a whole in value-based, value semantics-based UI updates that Compose does. And the recent addition to Compose, which is strong skipping, again, if you take a look at this from my prism, from my viewpoint, from value semantics viewpoint, it actually kind of assumes that all the types that are not known as stable, they actually follow value semantics, because strong skipping tells you that, well, actually, if the reference is the same, I assume that the thing has not been changed. I assume that the thing is immutable. You are not mutating it in place. And if there is a new reference, strong skipping assumes that the value definitely has been changed. So fundamentally, strong skipping says that for unstable types, I'm going to think that they still follow value semantics. They're still immutable. And if this assumption fails because your types that you're using with strong skipping, unfortunately, are not as such, then you would get some kind of a failure model. For example, if you have the same reference, but you in place updated it, you get a stale UI. which hasn't updated with the latest data. If you get a new reference, but the content is exactly the same, you do some extra work on recompositions that could have been skipped. And again, if you had value semantics in Kotlin built in, then that story with strong skipping would have been much better. So we talked about what value semantics is, and some of you might be thinking, OK, like, I understand what you're talking about, but who really cares? Is this really a problem if we don't follow it? Is this really something that is worth bringing into the language, is worth thinking about in your day-to-day life? Well, actually, yes, because value semantics really matters. And I'm going to show you 3 examples of bugs that happens when you don't follow value semantics when you actually should have. And these examples are not something that I have thought about, and it's not something that's coming from me. These examples are going to be actual examples from the internet, from well-known people and companies that show you all of that. So first, maybe some of you already read the blog post by Isaac about 2 mutables don't make a right. And this is kind of like your bread and butter example, and I think Compose documentation now has this specific example of what you should not do. So if you combine mutable state with in-place updates and you don't go correctly through this bridge, as I explained to you before, so if you wrap in a mutable state something mutable and you mutate the inner thing in place, actually the Compose will not see this update because from its value semantics viewpoint, nothing has been changed. It doesn't need to trigger anything, so you are getting stale UI. The proper fix is kind of like well known, and again, it's in the documentation there, that you should actually use immutable collections plus new values for those kinds of things, because they will not allow you to write code as in the first example on the slide. They will force you to always write their code as in the second example on the slides. And that will always work correctly. So again, if you use the bridge for reference types incorrectly, and you mutate the thing in place without going through the reassignment of the mutable state itself, you will get problems, and when I say problems, I mean you will have stale UI representation, and that is why adhering to value semantics matters, because there you just cannot have the situation with in-place mutation, because things are immutable, you would need to create something new, and Compose would have a chance to catch that. So a second example is from Uber, when they were very actively using auto-value and auto-value's immutable models. And it just happened that in their immutable models, a mutable portion sneaked in, where actually in one of the models, and this is a simplified example, in one of the models, the list that people were working on was actually an array list, which is, again, mutable in place, which doesn't follow value semantics, which is mutable. And the problem was that because you were sharing basically the same priced vehicle instance, and all of them shared the same array list, depending on which screen in your application did its update first or last, you were seeing very inconsistent data on different parts. And again, the fix was to adopt value semantics, to switch to immutable collections through, to be careful about that the data that you're working with, this data is actually immutable. And the third example, comes from what Spring advises you to do actually with this data. And this is something that, guilty, I wrote several times over back in the days when I was doing enterprise development, when you have some mutable data passing around through Spring layers or services or something else, and you just forget that this thing is actually shared, and you should not mutate it in place errorously. And if you concurrently at one service decide to update the thing and another read something out, you end up with a problem of basically data races, and that updates and changes in one layer, they corrupt another layer. And the advice from Spring Data and what you should do, it's spelled out like you should try to stick to a mutable object. Once again, you should fundamentally stick to using value semantics more and not less. And to sum it up, why value semantics actually matter, because it allows you to do a lot of amazing things. So for a compose case, it allows you to do efficient change detection and computation avoidance. So basically, recomposition mechanism is all built upon this thing. You don't have any shared mutable state if you follow that, and that means that the whole class of bugs that come with it, they're not possible anymore. And you don't get any cross-layer corruption. And another benefit that I didn't talk about this because there was not a good example of a bug here, but that it simplifies your reasoning, because going back to the original example about with defensive copying, if you definitely know that this thing is immutable, then that means that you can safely reason about what the state of this thing is, and you can be sure that no one can, out of order, change this thing without you knowing about it. And these advantages that value semantics fundamentally gives you, they are not something that academic language needs. This is something that a real industry language needs, because it helps you to avoid problems, as I've just shown you, that could happen in Spring, in Compose, and Uber also had problems with that. So now I've talked to you about what value semantics is and why you should follow it. I hope that some of you are by this point convinced that, yeah, probably we should be thinking about value semantics a bit more, about immutability a bit more, and we should be more strict about that. But you still don't understand why I was still talking about this. Okay, like, that's it, end of the talk. We are adopting value semantics. What's the problem? So the core kind of like problem about value semantics is how to do it properly. What I mean by that is that right now, I can stop the talk here, we can all go our ways, and you can do value semantics in Kotlin using regular classes. You have to be very careful to follow it. You have to always remember to use only vals. You have to always remember to use vals of the correct types. You don't get any convenient updates for these immutable structures. You would have to reconstruct them somehow using constructor calls, or you would have to write a compiler plugin that does some code generation for you that makes you a wither, or some other kinds of update utilities. And all of those manual steps mean that you can make a mistake. And making mistakes is something that Kotlin tries to help you avoid. And there is a story there, and the story is, again, already here. You can, instead of regular classes, use data classes. The thing is that they still need manual enforcement of you being careful about only using vals and proper types. But they improved the update story because you get a copy function, which makes this a bit more convenient. But you can still make a mistake. There are less possibility for you making a mistake, but it's still there. With value classes, you will get automatic enforcement of the things that are immutable, because you just cannot declare a var inside a value class. And you would also get this new copy var mechanism for implicit copying that I showed you on the first slide, and I'm going to show in more detail in a bit. So that means that the compiler, the Kotlin compiler, will be there in almost all of the cases to help you avoid not using value semantics when you said that you need it. And you say that you need it by saying that my data is actually a value class and it should follow this value semantics. And the main question here is how to do these updates, because we already have a mechanism in data classes with implicit copies. Why do we need this new mechanism? And the thing here is that, and this is a sneak peek into what language designers have to do in their work, like, most of the language features, you probably haven't thought about this because that's not your job, that's ours. Most of the language features actually fall somewhere on the spectrum of being very explicit versus being very implicit, and somewhere in between. And if you think about it really hard, most of the language features in most languages, they are somewhere within the spectrum. And explicitness and implicitness, they have their pluses and minuses. There are always trade-offs to all the decisions. Explicitness is super nice because you see what happens, you see it super explicitly. Usually the code is more verbose, but you do not get surprises. You exactly see what's happening in the code super explicitly, and some people consider this the main advantage. If you begin doing things implicitly, basically we're saying that the language will do some boilerplate for you. That's an oversimplification, but let's go with that for now. Then the code becomes more concise, it often becomes easier to read, but it could lead to surprises because what actually happens under the hood is hidden from you. And the thing is that Kotlin has made a conscious choice of introducing a lot of implicit things before, and it turns out that in a lot of the cases, developers are really happy with these implicit decisions. And I'm going to show you 2 examples of those things. So example number 1 is concurrency. So with concurrency, the traditional way before Kotlin introduced suspend functions, way pioneered by C#, technically by F#, and then popularized by C#, was you have to do explicit asyncs and awaits. So you have to basically explicitly say that, OK, this call is suspending. I know about it. I will await this. It will be explicit that here I suspend, await the result, and then I continue. So you have to manually write this await at every suspension point. Kotlin decided, and from what we've seen, this was the right decision, that in most cases you actually find with implicitly saying that every call to a suspend function is a suspending call by default. And basically, you don't need to sprinkle your code with async and awaits in most cases because it just makes sense. The second example about explicitness versus implicitness is type narrowing or smart casts or type checks, whatever you want to call them. So in Java, if you want to check that something is of a specific type and then use it as a value of this new type, now there are some improvements, and Java is also evolving as a language, but you still have to do an explicit binding. You have to come up with a new name. And if you have some nested things, you will, or things that over and over again type check different things on different types, you will have code with string, like object and object as string, or new string, new string, string 01, string 02, or whatever. And kind of like you have to come up with new names, and good names are actually hard to come by. Kotlin decided that, well, you already know that this thing has a name. It's an X. And now I know that this X is not just an object, not just an any, it's a string. Why do we force people to write a new name? We can just reuse the old one, and the compiler can take care for you implicitly that X is now known as a string. And this is a second example of Kotlin taking the implicit route, not forcing you to do explicit type narrowing, doing it for you. And people seem to be super happy with these things. But your question in the audience probably is, and what does value semantics have to do with all of this? Well, the thing is that right now we already have an explicit way of updating an immutable data structure, which is a copy. Lo and behold, you probably know how this code works and what it does, and it's super explicit, super visible in the code, super easy to reason about. Old value is untouched, new value is created. You explicitly control what is copied in which place and how it's copied. But this code is pretty boilerplatey once you begin working with deeply nested structures, because explicit updates, they just don't scale very well with nesting. And fundamentally, kind of like the intent, what you want to update here, I just want to update the city of an address of a customer for this specific order. It drowns in that you need to write all those things. And what's even worse, it actually creates some problems. So say that somewhere in your code, you have this snippet that says that, well, yeah, I need to recreate the order, I need to update the city, and I need, because I updated the city, I need to recalculate the value of the tax for this order that the person would need to pay. Code looks reasonable. The problem is that this boilerplate, it has hidden a bug, because the address that we're using for the text recalculation is still the old one. We've written the code how we expected it to work, because we wanted to batch updates in place, wanted to update this and that, but the update will happen only after everything is copied and assigned. And this thing reads the old address. And this boilerplate, this ceremony basically it lies to us. It says that like everything is going to be sequential, left to right, top to bottom, but it actually isn't because arguments that are siblings to each other, they don't see the nested updates for these kinds of code. And the nested copy is actually hidden from us what's happening in the program in which order. So that is a problem. Implicit copy design that we're going for with value classes, it doesn't have this. So for value classes, if you declare them, and if you want to update those, this thing will be expanded. You can think of it that it's going to be expanded in a bunch of copy calls. Actually, it's going to be a bunch of wither calls, as I said, that we generate for you. But the compiler implicitly under the hood will take this boilerplate and do this for you. And if you look at this code, I hope that it looks pretty convincing that it reads well, and it's super unambiguous what actually happens here. You have your order, and you're updating it with a new city. And how you actually do this under the hood, the explicitness, it's almost an implementation detail. You should not care about this. And the bug is also cannot be expressed with this style of copyvars, because if you want to update the text, first you update the address, then you recalculate the text and update the text. And it just does precisely what it does in the order that it does. So the code is sequential, actually, and it looks sequential. And you don't have this potential trap of the boilerplate of the nesting updates hidden that the update has not actually happened yet. Because this is the update. If it wasn't the line before, this update has already happened. Quote unquote, you kind of like mean exactly what you write. This thing is perfect, right? This is the best design ever, and there are no problems with it. Unfortunately, there are some problems. And the problem is that this thing creates some new puzzlers for you. And the core of the puzzlers is that if you read through this code and you see this assignment, right now in Kotlin, assignment means that the two things are now one and the same because Kotlin follows reference semantics at the moment. And when you say that, well, actually now some things follow value semantics, and when you update a thing, and you reassign the city, the order is actually unchanged, that is surprising for people. Because Kotlin developers and a lot of other developers, they live within the reference semantics-based world. But with value semantics, there is no reference semantics. There's value semantics. And the implicit copy that kind of like happens on the copyvar update or on the assignment, it kind of like breaks your expectations. And that is a bad thing. And we totally accept, and we agree with the feedback that I talked to you about in the very beginning, that this is not perfect. And the core problem here is the aliasing itself. So if you think about this, if there is no aliasing, so no one can point to no one else, then value semantics and reference semantics, they're indistinguishable, because there is no second reference through which you can observe that the copyvar update actually swapped the boxes. Once you begin having aliasing, the expectation that two aliases mean that updates through one thing are visible through another thing, this expectation is set in motion, and that's the problem. So a language that introduces value semantics, it basically, to avoid this, this puzzler, to avoid this problem, it needs to make sure that either you don't have aliasing when you're using copyvars, so then it's not visible, and the code remains unambiguous, or if there is some aliasing involved, that you explicitly opt in into this, and you say that, OK, I understand that at this point, actually, when I connect these two values, I actually understand that updates on one value are not going to be visible on the other value. And this can be surfaced as many different things. And by the way, we had similar hints for you with IDE markers for suspend calls and smartcasts. We have like the gutter icons for suspension points, and smartcasts are colored differently in IntelliJ IDs. These are all examples of these subtle hints that give you understanding and set your expectations right. For copyvars, we are going currently with some kind of a marker on the places where you introduce aliasing. So here, you're introducing aliasing for value things that you want to do an update later when you're doing new order equals order. And instead of a regular var, you would need to say that, well, actually I understand that this thing is going to be something on which I later do a copyvar update. I understand that at this point, I actually don't have any aliasing and the references are disconnected, and updates on one thing should not be visible on the other thing. And once you have this, then the problem becomes visible and expected, and it stops being a problem. Because the problem was broken expectations, but now we set the expectations right. We basically tell you that, OK, at this point, these two orders are actually disconnected from each other, and if you update one, you should not expect for the update to be visible on the other. And this is a minor addition on top of the value semantics and the copyvar updates that we believe solve this ambiguity problem and this incorrect expectations problem pretty nicely. But if you're not happy with this, if you're saying that I really don't like the implicitness at all, I don't like copyvars, they're a bad idea, you can still do things explicitly the same way as, for example, you can do with coroutines. If you don't like the implicitness, you can always use the explicit coroutine builders, and you can just do the same async await style as you would have done in C#, for example. So the default is implicit, and we believe it's good enough for most of the cases that you have. And if you need explicit control for whatever reason, it's still there. And for the value classes and the copyvars, the story is exactly the same. So if you're fine with implicitness, if you benefit from having the code that reads well, left to right, top to bottom, that is sequential and looks sequential, then you can use copyvars. If you don't like those, then you would still be able to use a copy function or some other utilities that either us or compiler plugins or you generate for you and work in this explicit style of value-based updates via explicit copies or explicit with the calls or something else. So again, when ergonomic cases are fine, you can use implicitness, and we believe that will be a good default. But if you really need, for some reason, fine-grained control, you can always still use it. So we're not taking that away from you. And I hope that that shows that implicit value semantics is pragmatic enough, because it helps you to avoid bugs. It makes your intent visible with the copyvar declaration on assignments. It is consistent with what Kotlin has been doing throughout the years, which is not forcing you to write boilerplate when you really don't need it, but still keeping the ability to do boilerplate when it's actually reasonable to do so. So yeah, it's an opt-in. You can use this, but if you don't like this, you can do explicit stuff as you did before. So to sum it up, value semantics gives you a lot of great things. It gives you freedom from some bugs. It gives you safer concurrency. It gives you better state management. It gives you simpler reasoning. And with the copyvar design, it also gives you ergonomic updates. But I forgot to touch upon one thing, which is, well, you're going to be creating more copies on objects, and more copies means worse performance, right? Well, now I'm gonna, in 5 to 6 minutes, put my money where my mouth is and actually show you that it's not that bad. The thing is that if you're working with value classes that don't care about identity, that gives much more opportunity for optimizations for your runtimes, for example, for the JVM. And JVM is already very good at skipping allocations when it doesn't need to allocate stuff, so it's very good at doing optimizations as scalarization and heap flattening. And Valhalla, which is coming soon, and there is already an early access preview build version for Valhalla for JDK 26 and 27, it actually makes these optimizations work out of the box and much more often for value classes. And yeah, I'm just going to show you a bunch of numbers and why they're awesome. Mandatory because I'm talking about benchmarks, mandatory mentions. This is done using a micro-benchmarking harness by Alexei Shipilov. The numbers that you will be getting are micro-benchmarks, so you have to understand why these numbers are happening and not just be happy with the numbers are small and numbers are large. And this is a preview build, so that means that the numbers probably will change in the future and for the better. But in some cases, you will see there is nothing better, that it's already great. And I will show you relative speedups. So what we're actually measuring, super simple thing. We're pretending that we have a record that holds some data. And the same thing, but it's a value record now. So we're saying that this thing follows value semantics. And I'm just going to updating in the weather style a bunch of things in a loop repeatedly. And I'm going to be doing the same thing both for the regular version and the value version. So if you really want to, you can drill down into the benchmarks and the actual results of the benchmarks that I got on my machine using this QR code. And there is a nice vibe-coded visualization for all of that. But I'm going to quickly show you the 3 most interesting results that we got out of it. So result number 1. For the copyvar case, where you're basically doing a object.x reassign to something new and recreate an object, actually using the wither call under the hood, what happens is that for a value thing, the additional allocations that you are paying go to 0. Because the value is local, it never escapes, the just-in-time compiler can completely erase all of the allocations and run everything on bare stack-allocated fields. And the same result applies not only for small loads, but also for very large value classes with a lot of stuff inside. It's still nothing extra is allocated, and the throughput improvements are pretty significant. So in this case, you are not actually paying anything extra. If you're nesting your value classes, so if you're doing a.b.c, in this case, like wrapper.object.x, assign something new, and you, again, recreate and reassign, are we paying anything extra there? Actually, also no, because if we definitely know the types of the things that we're nesting inside of each other, the JVM is smart enough, and this is actually what improved between 26 and 27 early preview versions. It got smart enough to optimize this case also for larger cases and for more different cases. And it also removes all of the extra allocations. So if you're using copyvars in Kotlin or this style of update in Java, but you're running on Valhalla, you are not actually paying anything extra. Larger cases are a bit worse, but there's still overall throughput improvements. Unfortunately, it's not perfect, because if you don't know that your type is definitely value, if you have a generic outer wrapper for your value type and you're doing some generic update, then you're actually paying more in allocations, because value classes at the moment are optimized not as efficiently as regular classes for these kinds of workloads. But surprisingly, the throughput actually is better. Why? Because once you're getting stuff out of the wrapper and you're working with this thing on the stack, you get local scalarization, and that actually helps locally with the performance improvements. So I hope this convinced you that actually value semantics is not expensive, and it actually saves you performance. And the important thing is that on JVM, we will have this. On other platforms, when the time comes, we'll have our own optimization stories. And the bottom line is, value semantics doesn't cost as much as you think. But I would like to encourage you to actually adopt and benefit from value semantics, not because it's an optimization, but because, as I've talked in the first part of the talk, it's a better story for how to write safer code. So you should adopt it for that, and not because the code will go brrr faster. That's not why you should adopt value semantics. It's basically literally a cherry on top, a nice bonus, but not the core thing why you should use value classes and copyvars in Kotlin once we have them. So to sum it up, why the hell did I give this talk? Because value semantics matter for Kotlin. We're going for the value classes and the copyvars as our way to represent immutable data and give you ergonomic ways of working with those. The first phase, hopefully, will be rolling out as experimental in 2.5, fingers crossed. And then as we progress with the design and we implement more and more of it, there will be additional things rolling out in 2.6 and so on. But the underlying thought, value semantics is great. I hope I convinced some of you that it's worth using it. But it's an option, it's not a mandate. If you're happy without it, then you can freely skip and not use value semantics. But even if you think like this, I would highly advise you to try to stop worrying about extra allocations, that the thing might look implicit, things might look foreign and unknown to you, and love value semantics, because this is something that we already do. It is very pragmatic, and it's actually, in a lot of cases, a lot faster than you think. So thank you so much for attending this talk.